Okay, so today we're going to be looking at our chapter on alcohols and their reactions. Now this is going to include some ethers and epoxides, which we already talked about, but we're going to be adding a little bit more to them. We'll do a few things with amines, and then the sulfur-containing equivalent to alcohol, which is thiols, which is just SH. Okay. So all of these are going to have similar reactions because they actually do behave quite similarly, and to some degree they're related to the alkyl halides, which we've already covered. So that's why we are just expanding on that. All right, now it's not as simple as just saying alcohols do the same thing as the alkyl halides, and it's mainly because the OH by itself is a terrible leaving group. Matter of fact, this equation we have is the exact equation we had going backwards in the previous chapters, where our bromine would have actually gone through a SN2 type reaction and the OH would replace it. It simply won't do that this way because the OH is too good of a nucleophile and it would actually always just go backwards. So the terms that we like to say is the OH is a terrible leaving group. So we are going to do something to try to make it better. One of the easiest things we can do to get a OH to leave more easily is turn it into a better leaving group. And a easy way to turn it into a better leaving group is to just protonate it, which is what we're doing here with HBr. So the HBr does come in here and it protonates our alcohol, making essentially a water. It is a cation, but the charge is right on the oxygen. And then simply by heating it up, we can let the bromine come in there and replace it. Now, this works with all of our, this works with HI and HCl as well. Might need to actually throw some heat in to actually guarantee it happens, but a lot of versatility here. Now, the mechanism is believed to be SN1 when we have a tertiary alcohol. And that makes sense because there's no way this is going to do a backside attack, or at least a bromine wouldn't be able to do a backside attack with this thing because that's tertiary. So SN1 is believed to happen. We just protonate the OH, we get the double bond, or we get a carbocation there, and then the Br attaches and we get a substitution product where the bromine is, or we might possibly get an elimination product, but we're not going to see too much of it because having HBr present, we would just do an addition of HBr right across of it. So we would only expect that product. And if we have a primary, we kind of expect this to be somewhat like an SN2 because we'll still protonate it. But now that we have our protonated OH being a good leaving group, that bromine can come in and do a backside attack and goes right on there. And there's plenty of evidence that says both of those are true. It's SN1 when you have a tertiary alcohol, and it's SN2 when you have a primary. Now, HCl turns out it's a little bit slower than HBr, HI, so we're going to make it stronger by actually putting a Lewis acid in with it. This Lewis acid helps form this nice little complex with our alcohol, where it's the OZNCl, and that actually leaves easier than just an HOH does. And it also makes this a little bit more electrophilic, so this bond's a little bit pulling more towards the oxygen. So now our Cl is a better attacking, or not our Cl, our CH2 is a better attack spot for our nucleophile. All right, now, interesting, most of the time what we do when we actually want to do stuff with alcohols is to turn it into alkyl halides and then do the same stuff in the previous chapter with any alkyl halide, just any old SN2. Biggest reason we don't start a lot of times with the alkyl halide then is simply because they're a little bit too reactive, so they have terrible shelf lives. So we actually do get alcohols in our stockroom, and we'll convert those to our alkyl halides first and then do a lot of stuff from there. All right. Let's do a couple practice problems. So I'm going to show you a potential problem because both these, if you look, are secondary alcohols. So we do predict that these actually behave somewhat like SN1, so we will protonate these first of all. But what we have to worry about now is when this leaves, it leaves behind a carbocation. That first one looks something like that. No problem, secondary carbocation, not expecting too much rearrangements there, so I would expect that Br just to go right on. And that actually is our major product that we predict. This one down here is a different story though. Having those two methyls right near it, when that carbocation gets created, there's a good chance it's going to do a little methyl shift. And if it does a methyl shift, we get a tertiary carbocation. And it turns out that does happen. One of our products that we get out of this mix is bromine there. And then we also do get it where it does actually attach here. We end up with both products. We get something where that secondary carbocation exists, the bromine attaches, and we do get the methyl shifts where this bromine moves down some. Carbocations will rearrange, so you have to watch out for rearrangements again. Now, the interesting thing is, even though this is a better carbocation, we don't necessarily see all of it go this way. We don't even actually, it's not even really safe to say that's the major product always, because it turns out the concentration of your HBr suddenly becomes a little bit of a playing factor on which one shifts your major product and minor product. It's a little bit outside the scope of our class, so right now we're going to do it, and you're just going to end up giving both products. And we will never be trying to identify a major product on the addition of HBr to a secondary carbocation or secondary alcohol. All right, we can avoid that by using a different starting ingredient. So phosphorus trihalides, along with pyridine, will actually do the exact same thing as HBr does, but it doesn't give us the rearrangements. Thionyl chloride down at the bottom also does the same thing. Now, the reason we don't get any rearrangements can be seen in the mechanism. So in the mechanism, our alcohol does attack the phosphorus instead of any acid, and that phosphorus tribromide forms this cool little complex. Now, it still needs to be deprotonated, which is why pyridine was mentioned there. See how it just says pyridine? Well, pyridine is a aromatic nitrogen-containing compound that's quite basic, and that will actually pull that away, yet this is not nucleophilic attack enough to actually interfere with our reaction. So it's just a great way of taking away H's. Now, once that's there, now the extra bromine that got kicked off here actually can do a backside attack SN2. So our advantages on a primary alcohol, don't have to worry about any rearrangements whatsoever because this is going to go straight SN2 on a good leaving group. Thionyl chloride does a similar thing. It just what gets attacked on the from the O is the sulfur itself, and you kick off a chlorine. We'll still deprotonate it with pyridine, and then a little bit later on, the chlorine will come in and do a backside attack. SN2 again. All right, so we're going to use that phosphorus trihalides when we need to avoid any rearrangements. We don't need to worry about rearrangements, just use HBrHI or HCl with that zinc chloride because it's cheaper and it's quick. If you have a tertiary, you're not going to have to worry about any rearrangements. If you have a secondary that can't rearrange, you don't have to worry about it. So there are times when we just choose to use HBrHI and HCl. All right, another thing we can do to activate our alcohols to make them into good leaving groups is make sulfonic esters out of them. Now, a common sulfonic ester is generated by something like a sulfonyl chloride, and we do just call them sulfonyl chlorides. They will have various different things on there, like a methyl sulfonyl chloride or ethyl sulfonyl chloride, but the sulfonyl chloride is just that SOOCl attached. The nice thing about this, if I put it in pyridine, has a similar mechanism to what we just saw, where the O does end up attacking the back of the sulfur, and then the chlorine gets kicked off. but we end up with what we're going to call a sulfonate ester. Esters, if you remember, were something more like this. Sulfonate esters just have an SO2 instead of that CO. All right. The nice thing is these sulfonic esters are going to make excellent leaving groups. This whole thing can leave quite easily. Doesn't really matter what that R is because we're going to try to do an SN2 type reaction on whatever this R is. Technically even SN1, so any substitution reactions, this becomes a good leaving group. The other plus, unlike alcohols themselves, which are terrible leaving groups, this is more comparable in reactivity to an alkyl halide, and yet it's a lot more stable than an alkyl halide. So we will see that we make this happen a lot more often, where we make the sulfonate chlorides. Now, these are some common ones that we actually use. This one is actually one we use on our campus, the para-toluene sulfonyl chloride, a little bit more shelf stable, and it is a powder. So it's very easy to deal with. All right. Now, a common thing we do with them, though, is once you've made a tosylate ester, you can just do a standard SN2 type reaction. And this is actually shelf stable. So these things could have been kept on the shelf if you wanted to make it in batches. And it will just be a straight SN2. It will also possibly be an SN1 because this is a good leaving group. So on a tertiary, you could do this if you wanted to. It's just typically on tertiaries, you don't need to because OH itself will come off with just a little bit of acid. All right. Now, here's where this comes into play, why we have these two different techniques just to put different nucleophiles onto a alcohol. The advantage of using the two different methods helps us out with our stereochemistry. Like, for instance, if we were to take an alcohol and react with PBr3 under pyridine, we end up putting bromine on, but the bromine goes in on an SN2. So that if I leave everything on this exactly the same, we would get an inversion. So a Br would now be coming out at you. So we just inverted that center. And then the OH, or the OCH3, does a backside attack there, and we end up inverting it again. So the OCH3 is exactly the same place the OH was. All right, but if I use a tosylate chloride, the tosylate esters, that does actually put the TS here, but it doesn't actually change the orientation. So this is still backwards. So now when the OCH3 attacks, it inverts there. So you get an inversion of the center where the OCH3 is. So we have two different ways of adding different nucleophiles on here, because this could be a nucleophile and that could be a nucleophile. But whatever we choose to add will cause an inversion or a maintaining of the stereocenter, because we got SN2 reactions. All right, next little reaction we're going to look at is an elimination. Now, we saw couple chapters ago that if you hydrate an alkene, you make an alcohol. And ironically, when we hydrate an alkene, if you remember, that was just add some water, and you used H2SO4 as a catalyst. And we didn't actually say there was any competing reaction. Turns out there kind of is. It is more of an equilibrium. It just happens to favor the alcohol side on a typical equilibrium. And the best way to get it to favor the double bond is to heat it up. You add heat to it, it favors the alkene over the alcohol. All right, now mechanism looks something like this. The H does get attacked by the O and does make a good leaving group. But this time when it goes to leave, instead of leaving and just going away, it leaves and then an adjacent H gets actually pulled off and you make your double bond. All right, now, because this is just a standard elimination, and technically the very first step, well, once we've created the good leaving group, looks very much like a standard E1 where we create a carbocation, you get the exact same products you get on any E1 reaction. So Zeitz favors the alkene with the least hydrogens off of it. So that would make it your major product. And this doesn't change it. Just doing H2SO4 with heat doesn't change this. You still get that same product. All right. Now, this would have been the exact thing we'd expect had this been chlorine and we did a standard elimination reaction. So that's actually what we're going to see here. Zeitz is the driving factor of what we get for our major product on all dehydrations of alcohols using acid. All right. Now, the dehydration is typically easiest on a tertiary alcohol as opposed to a primary. And that will probably make a little bit more sense if you think about what it's forming. Because if you go back up here, to here, we make a carbocation. So it makes sense that a tertiary would be easier because that would actually lead to a tertiary carbocation. And primaries, we might even expect they don't even do anything because we don't like making primary carbocations. And that is why it says it's hardest to dehydrate. There are special cases where you can get a primary, but we're going to have a better way to do a primary. Now, we do have to worry about rearrangement since the first step after we've protonated our alcohol is to make a carbocation. We will see rearrangements occur. There's not an easy way to avoid it if you're using acid and heat. Excuse me. Now, if you are doing E2 type conditions, you do have to worry about the possibility about the alcohol in there being a nucleophile on itself. So we would have that same type of thing when we make this into a good leaving group. But instead of a base coming in here and deprotonating it, we could have an alcohol, another one, come in and do a backside attack. And if it does that backside attack, we end up making an ester instead. And we have to worry about this happening. This is a nice little competition. Now, just like before, heat favors elimination, which is why we see heat applied to most of this all the time, because that tends to favor elimination. But there really isn't a good way to totally avoid it here. Whenever we're using acid with an alcohol, we are going to get mixtures of elimination products, and we're probably going to get some substitution products. Excuse me. Now, another problem we have is when we actually do consider that a primary alcohol should eliminate and make a primary or a terminal alkene, we're going to see that we have a small problem because this alkene in the presence of water and acid could turn back into another carbocation. And that carbocation that it would make here would be much more stable to make secondary. And if that were to do an elimination because of the heat we could actually see that double bond move. So 1-butanol, while it does actually react via E2, it's not going to stay that way because an alkene in the presence of water and acid does form alcohols and carbocations. So we do see this move around. All right. We also see some stereochemistry issues that pop up. Typically, if we have a situation where we can make a cis or trans, it's not right to say trans is more common. It is better to say our bulky groups get further away. So regardless of what I have attached or where the backbone goes, you want the bulkiest groups as far away from each other as possible, leading toward the major product. But more interesting, typically if you get this type of reaction, we're going to look at all the possible products and not necessarily just the major product. Okay, turns out we can avoid this. We don't have to, if we use acid on something like 2-butanol, we're going to end up with some 1-butene. We're going to end up with some 2-butene. We might even end up with some esters where the, I guess that would be sec-butoxy gets attached to another butane. But we can avoid it using POCl3. So POCl3 with pyridine actually does give an elimination product. It gives mainly the Zeitz product. mechanism can show you why we don't have to worry about some of those rearrangements. Turns out the phosphorus gets attached to the O, and then we actually deprotonate that O. But this thing as a whole is an excellent leaving group, and it's super bulky, so it's in the way for any substitutions. So it favors that pyridine coming in there and ripping off a nearby H and forming a double bond. Now, the plus is your double bond ends up starting exactly where the OH was, so we don't have to worry about it moving around. Okay, other thing we can do to eliminate the possibility of rearrangements is to turn that OH first into a tosylate chloride. So if I, or mix it with tosylate chloride to make a tosylate out of our alcohol. Now that it has that OTS on there, which is a great leaving group, we can actually choose a nucleophile that favors elimination. Now it's showing OCH3 here, and OCH3 is a strong nucleophile, and we could suspect it might be capable of doing SN2 type reactions, but this being tertiary, there's no way that's going to be doing any SN2. So E2 is favored, and you do actually end up making the most stable Zeitzief's product. Okay, next thing we're going to look at is our oxidation of alcohols. Now we're going to do it mainly, we're going to introduce it using chromic acid. There's two ways to actually write chromic acid. This and this both actually are equivalent to us. They both basically say chromic acid. Now what chromic acid is going to do to an alcohol, it's going to remove an H off the alcohol and an H off the adjacent carbon and form a double bond. And that technically happened here. There's an H drawn there that just wasn't drawn. It just eliminates them. Secondary alcohols always get turned into ketones. If it's a primary alcohol, primary alcohols have two hydrogens on that adjacent one. The very first step is to remove one of those hydrogens off both, and you end up with an aldehyde. But it turns out aldehydes can also be oxidized with chromic acid into carboxylic acid. Matter of fact, chromic acid is strong enough that we never even try to stop here. It's basically safe to say if you got chromic acid with an alcohol, you're getting a carboxylic acid. If you need an aldehyde, you actually can use this stuff called PCC. It is a chromic acid derivative, and we are fine to call it PCC. It's only really ever used to turn primary alcohols into aldehydes. Now, interesting, nobody really likes to use either one of these too much because chromium is toxic. There are alternatives. All right, but before we see alternatives, we got to ask ourselves, why can't tertiary alcohols be oxidized? Well, chromic acid, when it was looking for an H off this carbon. Since there's no H's off that location, this H can't be ripped off. So tertiary alcohols cannot be oxidized. All right, our alternatives to chromic acid, and I get a kick out of this. Every single organic textbook on the planet still talks about using chromic acid and PCC, yet NaOCl will also do the exact same thing. Got to keep it cool because if it's hot at all, it over-oxidizes or under-oxidizes depending on your component. So 0 is a good temperature to keep it at, and it is just N vinegar. But if this thing works so well, what the heck is that? Turns out that's the active ingredient of household bleach, sodium hypochlorite. It's relatively safe compared to chromium. Still wouldn't want to have a lot of it around, but it's actually a little bit easier to do. The mechanism there is a little bit more understood. So the H on the hyperchlorite, sodium hypochlorite, the HOCl, still does actually go on there and make the OH into a good leaving group as water. And then the other OCl comes in and does a nice little backside attack, and we end up making this nice little complex. That is going to favor the bromine ripping off, or a base ripping off that H, forming a new double bond there, and then kicking off the chlorine. Now, our chromic acid and the OCl needed acids added to them. Now, if I had had something else on this molecule, like a nitrogen somewhere that had a lone pair, that H is going to react with that nitrogen and never actually do anything at all for alcohol. So when we have acid-sensitive compounds, Swerin oxidation is the one to go to. Now, Swerin oxidation use this DMSO, as dimethyl sulfonate. It smells of rotten egg, so this actually does kind of smell pretty bad. And as it goes forward, it actually kicks off carbon monoxide. So it's not necessarily a good alternative, but it's the only way we can do it if we have an acid-sensitive alcohol. All right, on to esters. Now, we've already talked about esters, and we even saw how to make them back with our alkenes chapter. Turns out they kind of behave in many ways similar to our alcohols, just because the O can still be activated and turned into a good leaving group. Instead of making water as a good leaving group, when you activate it, you make an alcohol as the leaving group. Now, interesting, see how this is just HI and heat? Turns out that alcohol that's being formed, if we actually put it with some more HI and keep on heating it, we end up actually replacing that OH with I. And then we end up making some water as our other product. So typically we see this written as 2, and then we get R I and R prime I, and then just some water. About the only way that stops is if our ether actually has a benzene in it. If I do this, I will get that R, and I'll do this, HI in excess. If I do that with that particular ether, this ends up staying as phenol, because phenol is quite stable by itself, and then the R just ends up with I, but it doesn't continue to go on. All right, but while that's similar, and it does have a similar mechanism, because we are still making a good leaving group out of our OCH3 or our OR, we have very similar responses to HI and HBr and HCl. Where it does fail, though, is we can't actually make a good leaving group out of it with the tosylate. So if we try to make a tosylate ester out of an ether, this last step here can't really happen. We can't have that Cl come in there and remove an H and leave us a good sulfonic ester, because there's not an H there. And that Cl is not going to be able to rip off an R. So this doesn't actually ever turn into a good leaving group. So the only way to get ethers to behave like good leaving groups is to do it under acid conditions. But since ethers really only react with acids, HXs in particular, we end up using them a lot as solvents. And almost all of our major solvents that we actually mentioned throughout this chapter, this semester, THF, ether, THP, DME, they're just ethers. We use these abbreviations just because they're a little bit more common. Okay, epoxides, something else that we did. Now that first reaction up above is how we introduced making epoxides in our alkenes chapter. If we took an alkene, react it with a peroxy acid, you made an epoxide. We did this back then with PBA, peroxybenzoic acid, and MCPBA. And back then we didn't necessarily care what the structure was, and we still kind of don't. We just know we're going to use a peroxy acid to make an epoxide. Turns out there's another way we can do it. Now, we know this first step. Back in our alkenes chapter, we talked about adding chlorine and water to an alkene, and you got chlorine and OH in a transposition. Well, it turns out if you make that hydrohalon and then treat it with some sodium hydride, you can deprotonate that alcohol, make a very negatively charged base form of it. Well, this neat thing will now do a backside attack to that chlorine and make an epoxide. And the only thing you have to do to your halohydrin is add some sodium hydride to it, and you now have another way to make an epoxide. All right. When we first introduced epoxides, we showed opening them. We did it with just acid and water. Here I'm using acid with some Br in it. And it does the same type of thing. So the O does attach to the H, and we make a cation of the epoxide, and the bromine does attack, and we end up with a bromine on one side and OH on the other. And there's not really anything that changes about that if we actually add more things to it. We still get an OH on one side and a Br on the other. But if we actually change and put a different nucleophile in there, a better nucleophile ends up attached rather than the Br. So we could safely say this is any nucleophile. And almost any nucleophile will attack the backside of that protonated epoxide. Now, if our epoxide is asymmetrical, what I mean by that, got a methyl on one side but nothing on the other, we're going to see that our nucleophile ends up going to the side with the more substituents most of the time. That always leads to our major product. The nucleophile goes to the side to the carbon with the most things added. All right. Now, turns out we can get the ring to open up under just basic conditions as well. We can just do a straight S into attack to the ring, because the ring will be slightly positive. So a nucleophile, a strong nucleophile, will just do a backside attack. And then anything with some H's around it, more of put this in with some alcohol in there of that same thing, and the H will protonate it, and you end up with a new substituted product. But this time, because this O is a strong nucleophile, it favors an SN2 type mechanism. It's going to go to the side of this that's least substituted. So this way, your nucleophile ends up on the side that was least substituted. So our nucleophile, we can choose which side we go to, whether or not we're acidic or basic. Under acidic conditions, you go to the side that's more substituted. Under basic conditions, you go to the side with less substitutions. Okay. Excuse me. When we actually first introduced this wonderful product of adding acid to our alkenes, we had to worry about rearrangements of our carbocation. That's what we're showing on that top one. If I actually wanted to add an alcohol or an OH to that bond, if I put it in with acid, I would rearrange it, and I ended up making a tertiary alcohol all the time. There was no way to get just the OH to stay on that on near where that double bond was, because it was going to rearrange. We introduced this back in our alkenes chapter. If we actually made an epoxide of that ring, we wouldn't have to worry about it rearranging. It would actually go where that is. Now, instead of opening that ring under acidic conditions with a nucleophile, if we actually just take this epoxide ring and treat it with NaH, it will actually add an H to the side that's got more H's and leave that as a no negative. And now we can actually protonate it. So we actually can put an OH right near that where that double bond is by just using MCPBA and then some NaH. All right, next thing we're looking at is our diols. This top method is something we introduced in our alkenes chapter, and that is making transdiols. Back then we did it with water and acid. Here we're just doing it with OH. Both ways work. OH, we'll put it on there and it'll be translocation. Then we just need to protonate it and we get a transdiol. Now, another way that we could actually make our diols would have made cis diols. Back in our alkenes chapter, we did this with cold KMnO4. Here we're introducing osmonium oxide, which does the same thing. It's a little bit less toxic, so it's a little bit easier to work with than the KMNO4. Okay, next thing we're looking at is a weird little thing that happens in biological systems. And your book just introduces it now because it helps explain something that's been going on with all these nucleophiles and whatnot. When something like a benzene ring or a aromatic compound gets into a mammal or almost any biological system, the first thing that your body wants to do to break it down into something that can do something with or get rid of it would be to oxidize it. Now, it's your biological system's goal is to turn this benzene oxide into phenol. And technically, this is just a rearrangement that happens. And it does happen relatively easy enough. But where this gets to be a problem is the stability of this epoxide might be stable long enough that a nucleophile could attack it. Nucleophile is just anything with a pair of electrons on it, and we get this new substitution product, which would actually eventually get an alcohol added to it. Now, when this happens is if we've done something to this ring, biologically speaking, or what we got in there, that makes this epoxide more stable. If the epoxide is stable enough to stay like it is, we see nucleophilic substitution happen a little bit more often. If it's a little bit less stable as an epoxide, it rearranges a lot quicker. And that is something we want on most biological areas. We don't want the nucleophile attack. All right, now an example where this actually plays in, why it makes it more stable. So I have this naphthalene oxide. It is breaking this aromatic properties by making this epoxide, but having this other ring over here that's aromatic, naphthalene oxide is a little bit more stable. So it will exist long enough for a nucleophile to attack. And technically, this particular one could make two different nucleophiles. We're going to put H on the epoxide and make either a cation here or a cation here. Now, the reason this one up here is more stable is because it does resonate back and forth. And then we'll just actually end up ripping off that H that's here and make another double bond, and we get this one naphthol. But on this lower one, the only way to make this cation more stable would be to borrow that charge from here, which would destroy that aromatic properties. And just doesn't happen, so that's why we only see that at about 10% of the time. All right, but something like this can be bad for us because as a mammal, I don't want the naphthalene oxide to be stable enough for a nucleophile to attack, because in our bodies, our nucleophiles are things like DNA, RNA. Almost any nitrogen in your body that has a lone pair could actually behave like a nucleophile. And if our arene oxide happens to be near something like our like this deoxyguanosine, we're going to actually make a bond there. And this now is no longer what it's supposed to be. Your body can't replicate it. That is what makes arene oxides potentially carcinogenic. So naphthalene is actually something that would be safe to call a carcinogen because it's going to stay with that epoxide a little bit longer because this thing is more stable. If it was only able to go to a less stable condition, it's going to rearrange to a phenol a lot quicker. So more complex rings, if I lose that one little bond to make an oxide here, we still have 1, 2, 3, 4 rings that are aromatic. Even down here, rip off this one, we still have 4 rings that are aromatic. That makes a very strong carcinogen, just way too stable as an oxide. Therefore, it's going to get attacked by nucleophiles a little bit too easily. All right, what's next? Amines are going to be introduced now because that nitrogen on amine actually seems like, well, kind of like an O. Seems like we could protonate it, make it a good leaving group, therefore we could do a backside attack. So we're going to actually add it in here just to actually complete this picture. Turns out it's not very reactive at all towards substitution or elimination. And it's mainly because we're starting to actually be too weak of an acid once we've put an H on there. So an NH3 is not necessarily a good leaving group, or not nearly as good of a leaving group. So we're going to see that they behave totally differently. All right, forget about that. So we can get them to behave as nucleophiles, but rather than actually doing a full SN2 where they fully replace things, they do this weird little thing where when they go in there and attack, they keep all their H's together. So we end up making a stable quaternary amine, or a charged nitrogen. And even on something like our epoxides, nucleophilic, this is also basic, so we'd expect to go to that least substituted side. We get it down there, and this O negative and N positive are actually going to exist like that, but they are potentially going to rearrange and get the charge neutralized. Elimination's a little bit different picture here. So we can actually make quaternary ammonium salts easy enough just by getting R groups added. Once we got it up to a quaternary salt, when we heat it up, we form an elimination product very easily. But we form a very particular elimination product. Technically, we're breaking that bond right there and forming a double bond starting on that carbon. Well, this carbon's always going to be on the end. So our Hofmann elimination always makes a very unsubstituted double bond for the most part, because that end location is likely going to have some hydrogens on it or whatever it is, but it also it almost always forms a double bond starting right there where that nitrogen was attached. Matter of fact, if we were to look at these two products and talk about them being formed, a double bond with 3 hydrogens versus double bond with one, we would actually refer to this as more of that Zaitseev's product, because Zaitsev said we always made an alkene that formed with more H's. Well, Hofmann products always favors a less substituted one, because we're going to break it off right, well, that's not there. We're breaking off right there, and we're either going to form a double bond here or here. Those are our 2 beta locations, but this is going to be right there at the end. Hofmann always favors the least substituted. So our major product is always going to be the double bond that has the most hydrogens off of it. And we actually will see this called the Hofmann product. So Zaitsev is typically the double bond with the least hydrogens off of it. Hofmann is always the one with the most hydrogens off of it. Okay, and the biggest reason it is the most is because it's just actually a little bit more stable when we put our charges out there. All right, last little functional group we're going to talk about here are our thiols. Thiols get their names very similar to alcohols. Alcohols, you would actually just name the backbone and add an OL at the end to represent a thiol, or an alcohol. To represent a thiol, you add a THIOL. And nomenclature priority, they're right there with alcohols, so they have more priority over our alkenes and our alkyl halides and the esters, but they have a lower priority than alcohol. So if I put that with an alcohol, like this last one, that becomes a substituent, and mercapto is the name of an SH. So 2-mercaptoethanol is IUPAC, as is a little bit more modern 2-sulf and eel ethanol. I'm going to write that because I wrote that too small on my paper. ANYL. ethanol, all one word. Now, reactions of thionols are very similar to OHs. They're actually stronger OHs, so therefore they actually form better nucleophiles. So we will see that an CH3S is actually more reactive as a nucleophile, so it will do SN2 easier. We will also find that we can make sulfonyl salts kind of like our quaternary ammonium salts. So we can actually react CHI, for instance, with a thioether, and we actually can add another CH on there and make a charged species. And this is actually stable enough that it will actually combine with the iodine, and you can actually make sulfonium salts as nice little solids to move away. Typically, that's what we end up doing because most thioethers stink. They have that little rotten egg smell, but if you make a sulfonium salt out of them, you lose that aroma. And if I want to turn a sulfonium salt back into a thioether, I really do just need to add a base to it. If I add a base to it like OH, I will make one of the things that are on the sulfonium salt come off with the alcohol, and the other ones will actually stay on the thioether. All right, that finishes us up with this chapter. There are plenty of things to practice in there, so exhaust the book, look over your worksheets, and fire me up with any questions you possibly have.